Section 5.3, we're interested in the idea of definitions of b to the 0 and b to the negative n. So we notice that if we took 3 to the third, that's equal to 27. If we take 3 squared, that equals 9. 3 to the first equals 3. 2 cubed equals 8. 2 squared equals 4. 2 to the first equals 2. So we notice that if we wanted to define 3 to the 0th and 2 to the 0th, we always want to follow a pattern. We notice going from 3 cubed to 3 squared, we divide by 3. So 27 divided by 3 is 9. From 3 squared to 3 to the first, we divide by 3. 9 divided by 3 is 3. And so to get from 3 to the first to 3 to the 0th, we divide by 3 again to get 1. And then we notice that going from 2 cubed to 2 squared, we take 8 divided by 2 to get 4. From 2 squared to 2 to the first, we take 4 divided by 2 to get 2. And so we get from 2 to the first to 2 to the 0th, we get 2 divided by 2 is 1 again. And so it turns out b to the 0th is equal to 1 for all b not equal to 0. So it turns out that 0 to the 0th, oddly enough, is undefined. Pretty much this winds up being because we don't know whether we'd like a to the 0th to be 1, but we'd also like 0 to the nth to be 0, and so we can't decide which one 0 to the 0th should fall into. So 0 to the 0th is undefined. So otherwise, we know b to the 0th is always 1. So if you see 3, we already did 3. If we did 5 to the 0th, that's 1. And so it's actually kind of convenient because if we have 2,473,409 to the 0th, it doesn't matter how big the number is. If it's the 0th power, we get 1. We also notice this is helpful for exponential expressions. If we have x to the 4th y cubed divided by z to the 7th to the 0th power, again, we just get 1 as long as x, y, and z are in 0. So as long as x, y, and z are in 0, we know that expression to the 0th power has to be 1. And that if x, y, or 0 is 0, that causes other complications. So a little more interesting is the idea of b to the negative n. We notice that, again, we can look at patterns. We notice that if we're saying 2 squared is 4, and 2 to the first is 2, and 2 to the 0th is 1, again, following the pattern, we should get 2 to the negative 1. As we go down 1 in exponent, we are dividing by 2 each time, we should get 1/2. And if we said 2 to the negative 2, we would get 1 divided by 4. And so it turns out that b to the negative n is the same thing as 1 divided by b to the positive n. And this winds up being very helpful. So if we saw 2 to the negative 5th, we know that's 1 divided by 2 to the positive 5th. And we can actually go the other direction as well. If we happen to see 1 divided by 3 to the negative 4th, we know that's going to be the same thing as 1 divided by 3 to the 4th. And now we can multiply by the reciprocal. So we get 1 divided by 1 times 3 to the 4th divided by 1 gives us 3 to the 4th divided by 1, or just 3 to the 4th. So in practice, what we end up noticing is that if we saw x to the negative 2 divided by y squared, we could write that as 1 divided by x squared y squared. If we saw x squared y divided by z to the negative 3, we could write that as x squared y z to the third. So anywhere we see a negative exponent, we can just move it to the other side of the division bar. And so, sort of worst case scenario, if we saw something like x squared y to negative 3 divided by x to negative 3 y squared, we notice we could rewrite that as x squared times x to the third. We just move the x to negative 3 to the numerator as a positive exponent of 3, divided by y squared y to the third. We take that y to the negative 3, move it to the denominator as a y cubed, and so we get x to the fifth divided by y to the fifth. So let's look at one more example of that, just to make sure that's working right. If we had x y to the negative fourth divided by x to the fourth y to the negative 2, we notice we've got a couple of options. We could write that as xy squared divided by x to the fourth y to the fourth, and then simplify that. We could think of that as being 1 divided by x cubed y squared. We also could think of it as being x to the 1 minus 4 y to the 2 minus 4, which would give us x to the negative 3 times y to the negative 2, which is still 1 divided by x cubed y squared. And so it's a question of which method feels more natural. So you'll actually notice if we had, we're using x too much. We'll look at if we had a to the fourth, b to the negative 7, divided by a squared b to the third, we notice that an easy, I should say straightforward approach is just think of that as a to the 4 minus 2, b to the negative 7 minus 3. So we know we can just take b to the negative 7 divided by b to the third is b to the negative 7 minus 3, and we get a squared b to the negative 10th. And then if we want to write it without negative exponents, we can write that as a squared divided by b to the 10th. So winds up being pretty straightforward. So in general, just to clarify, whenever we've got b to the negative n, we can write that as 1 divided by b to the n, or 1 divided by b to the n, as long as b is not 0. Obviously, if b is 0, we have so if we mix that with our other exponent properties, we notice that if we had something like 3x squared y to the fourth to the negative 2, we know we can write that as 3 to the negative 2, x squared to the negative 2, y to the fourth to the negative 2, gives us 3 to the negative 2 times x to the negative fourth times y to the negative eighth. And so if we don't care about negative exponents, we could possibly leave it that way, but we notice that at the very least 3 to the negative 2 we should write as being 1 divided by 3 squared, and then it's probably helpful to write that as 1 divided by x to the fourth and 1 divided by y to the eighth. And so we get 1/9 times 1 divided by x to the fourth times 1 divided by y to the eighth, or we could write that as 1 divided by 9 x to the fourth y to the eighth. If we try something a little bit different, if we had 5 x to the negative 2 y to the third to the negative 2, we notice now some things are going to wind up being in the denominator, some things in the numerator. We're going to get 5 to the negative 2, y to the positive 4, x to the positive 4, y to the negative 6th, and so that's going to wind up being x to the fourth stays in the numerator, but then we'll get 5 squared and y to the 6th in the denominator. You notice as soon as it goes to the other side of the division bar, the exponent sign changes, and so we get x to the 4th divided by 25 divided by the 6th. So kind of our worst case scenario would be something like, what do we look at? We'll look at x squared y to the negative 3 z to the positive 2 divided by x y to the negative 1 z to the negative 4th. We notice that worst case scenario, we could look at that as x to the 2 minus 1, y to the negative 3 minus negative 1, z to the 2 minus negative 4. That would give us x to the 1st, y to the negative 2, z to the positive 6, and so we'll get x z to the 6th divided by y squared. Now another one that comes up fairly often is if we saw something like x y to the negative 2 divided by z to the negative 3 to the negative 1, we notice we have two ways of doing that. Because it's to negative 1, we could just write it as z to the negative 3 divided by x y to the negative 2. We can just flip it. And then simplify it from there. So that would wind up being y squared divided by xz cubed. So we're just noticing z to the negative 3 becomes z to the positive 3 in the denominator, and that y to the negative 2 in the denominator becomes a y squared y to the positive 2 in the numerator. Alternatively, we could have written it as x to the negative 1, y to the positive 2, divided by z to the positive 3, and then we would have had a little bit less work. We would have gotten getting y squared divided by xz cubed. So the question of which way is going to be easier generally depends on the problem, and it's often not easy to tell which way is going to be easier until you've actually done it.